Now let's talk about atmospheric pressure. So first of all, an interesting question which is not really relevant for this particular chapter is why do we have an atmosphere? Now, you might, um, if you think about it, an atmosphere is just some gas which seems to be stuck to the surface of our planet, right? The atmosphere goes up for about 100 kilometers above the surface of the planet, um, and it progressively thins out. And so at 100 kilometers, you will hardly detect any atmospheric gas at all. The atmosphere is much thicker as you get closer to the surface of the Earth. In fact, um, 50% of the atmosphere is below about 6 kilometers from the surface. So you can see that it's a lot thicker near the surface, and it gets thinner and thinner and thinner as you go further out. Okay, so the question was, why do we have an atmosphere? Why didn't the atmospheric gases just sort of diffuse away and just go out into space? The correct answer is because of gravity. So we're going to learn in chapter 13 that there is a certain speed, minimum speed that an object must have in order to escape the Earth's gravity, and that's called the escape speed. If you look at the average speeds of the molecules in our atmosphere, it's much less than the escape speed needed to escape the gravity of the Earth. And as a result of that, the Earth has an atmosphere. Um, the moon has a much weaker gravity, and so the moon doesn't have any atmosphere because its gravity is not strong enough to hold on to the atmosphere. What is our atmosphere made up of? It is mostly made up of nitrogen and oxygen. Nitrogen and oxygen. Nitrogen, I think, is 71% or something like that. Or let me just quickly Google that because I never remember. Yeah, the nitrogen is 78% of the atmosphere. The oxygen is 21% of the atmosphere. That leaves about 1%, and that remaining 1% is mostly argon. And then there are trace amounts of other gases like carbon dioxide, water vapor, methane, and so on. Okay, but the atmosphere is mostly nitrogen and oxygen. Okay, so we live at the bottom of this ocean of atmosphere, and so the pressure exerted by the atmosphere on us is what we call atmospheric pressure. Okay, what is the value of the atmospheric pressure? Um, you could you could measure it by just taking. In principle, you could measure it by just taking a sheet, flat sheet, measuring its area, and then measuring the force that that sheet is feeling as a result of the atmosphere, and the pressure would simply be force divided by area. So if you do that, you would get the value of the atmospheric pressure would be approximately 101,300 newtons per square meter, or 101,300 pascals. Sometimes it's expressed in kilopascals, so in that case it would be 101.3 kilopascals. And this amount of pressure is usually called an atmosphere. That's also another unit of atmosphere, another unit of pressure, the atmosphere. Okay. Another unit of pressure that you might be familiar with is PSI. So that's pounds per square inch. You know that pressure is simply weight force divided by area. So if you measure force in pounds, and if you measure area in square inches, then you can get a new unit of pressure. It's pounds per square inch. That's called PSI. So in PSI, that's about 15. The atmospheric pressure is about 15 pounds per square inch. Right? Okay. Is this a large pressure? Just imagine that I have uh, a sheet of paper which is 10 inches wide, a square sheet of paper which is 10 inches wide and 10 inches thick. So 10 inches long, 10 inches wide. So what is the area of this? So it's going to be 100 square inches. What is the atmospheric pressure on one side of this sheet? So it's the atmospheric pressure is 15 pounds per square inch. So the force exerted by the atmosphere on this sheet of paper is going to be 15 pounds per square inch multiplied by 100 square inch, which is going to be 1500 pounds. So if you just imagine holding a sheet of paper which is 10 inches long by 10 inches wide, on one side of that sheet you have 1500 pounds of pressure, of force acting as a result of the atmosphere. So how are you able to move that sheet? Why is it not pinned to the ground all the time? The answer is the 1500 pounds of force we just calculated is acting down on the sheet because we're using this area, but it's also acting from the other side. You have the same 1500 pounds of force acting from the other side. And since you have the same force acting from both directions, the net force on this is zero, and so we don't notice it. Okay, so that is what I meant when I said that we don't ever notice the atmospheric pressure just because the atmospheric pressure is everywhere around us, right? So it's only when the pressure becomes different from atmospheric that we begin to notice it. One rather amazing example of that is the following. There was once an incident where one of these oil tankers it's a train whose with cylindrical compartments like this, which transport oil or other fluids. So a cleaning crew came in one night and they steam cleaned the inside of the apartment, and then they closed it. And remember that since this transports fluids, it's absolutely watertight. So they, after steam cleaning the apartment, the compartment, they shut the hatch and airtight hatch and left. And what happened the next day was this. This is what it looked like. Now, this is not the actual incident where this happened. This is a video recreation of it where they do the exact same thing, and I'll let you watch that video. You can probably watch it better on your own computer. So what they did here was they filled this with steam and then just shut it and let it cool. And you can see how it implodes. So why does it implode like that? When it was being steam cleaned, the entire compartment was filled with steam, right? So the steam displaced the air and took its place, and so that most of the compartment was filled with steam. All right, then they closed the hatch, right, and left. So what happens to steam when the temperature gets cooler? It condenses to droplets of water, right? And so inside the compartment, all the space that was being taken up by the steam has disappeared and now is transformed into droplets of water. So there's a lot less gas inside than there was before, right? And so the pressure inside is lower than atmospheric. The pressure outside is atmospheric. So what happens is that there is a pressure difference between the inside and the outside, right? And if you multiply that pressure difference by the area of the compartment, then you get the force, right? and the compartment is pretty large, so the area is large. uh, the pressure difference can be, the pressure inside would be very small, right? So the pressure difference would almost be, it would be P atmospheric minus some very small quantity. So approximately P atmospheric multiplied by area. I'm using an approximate symbol here. And so the area is large. The P atmospheric is pretty large, 15 pounds per square inch. So that would be an enormous amount of force acting on the compartment. So this is the net force acting on the compartment. There would be an enormous amount of force acting on the compartment, and that is what crushes it. So hopefully that's clear. Okay, now the next thing that we're going to talk about is how do you measure atmospheric pressure. So a device which measures atmospheric pressure is called a barometer, and barometers have been in use for a very, very long time, since the mid 1700s. The first barometer was invented by Torricelli, and the way it works is the following. Okay, so let me move the diagram over here. So so to understand a barometer, just imagine that you have a tube which you fill with mercury, like here. And once the tube is completely full, there's no air bubbles or anything, you plug the tube, invert it, and put it in a pan of mercury, right? So you would find that some of the mercury now begins to flow out of the tube and fill up the pan, but the mercury stops flowing once its height reaches about 3/4 of a meter, like 76 centimeters. So this height is approximately 76 centimeters. This is something that surprised Torricelli when he did this experiment for the first time, because he probably expected that all the mercury would flow out. But he was surprised to find that all the mercury doesn't flow out. Once the height of the mercury column in the tube reaches around 76 centimeters, it stops flowing. Now, why does the mercury stop flowing out once its height is 76 centimeters? Let's try to understand that. So let me draw this vat of mercury over here. Let's draw this tube. And what we just said is that the mercury level will not fall further beyond, this is all mercury, 76 centimeters. So let's call this height H. I'll use a different color here. Okay, now let's try to understand why the mercury isn't flowing any further. Consider a point over here and another point over here. Okay, what can you tell me about the pressures at these 2 points? Clearly the pressures have to be the same, otherwise the liquid would flow, because liquids always tend to flow from high pressure to low pressure. So if this point is A and this point is B, I'm just writing the A and the B a little bit further away, just not to clutter the diagram. I could just write them here, A and B. So if the pressure at A and the pressure at B were different, then the fluid would continue flowing, right? But since the fluid is no longer flowing, I can say that the pressure at A is the same as the pressure at B. Since the fluid is not flowing. Okay. All right. Now, what is the pressure at B? So pressure at B is simply atmospheric. Why is that? Because B is in touch with the atmosphere, right? What is the pressure at A? The pressure at A is caused solely by the column of mercury above it. So what is there above A? So there is the column of mercury, and then there is this empty space that doesn't exert any pressure. So the pressure at A is caused solely by the column of mercury that's sitting directly above it. We know how to calculate the pressure due to pressure at a certain depth underneath the surface of a fluid. So that is going to be pressure at the top plus H rho g, the formula that we just derived. The pressure at the top of our mercury column is 0 because there is empty space above it, right? So it's just going to be H times rho mercury times G. So you get this equation for this arrangement, and you can see that the height of the mercury column is a nice proxy for the atmospheric pressure, because the rho hg and rho hg and g are constants. So if the atmospheric pressure fluctuates, that will be reflected in a change in h. So this arrangement that I have over here is a barometer. It's a device which will always tell me what the atmospheric pressure is. I just need to keep an eye on the height of the mercury column. And so, in fact, this is how barometers worked for a very long time. Nowadays, of course, there are more sophisticated ways of measuring pressure. But this is the principle of a mercury barometer. And here is a mercury barometer, which is just made a little bit nicer than my diagram, so you can easily read off the pressure. Okay. So you can see that, so it turns out that normal atmospheric pressure corresponds to about 76 centimeters of mercury. You can easily calculate that if you set P atmospheric to be the normal atmospheric pressure, which is 101.3 kilopascals. You can look up the density of mercury, you know what the value of G is, so you can solve for H. So you can find that for normal atmospheric pressure, H is about 76 centimeters. And that inspires a new unit of mercury. We've seen plenty of units of, new unit of pressure. We've seen plenty of units of pressure so far. It's the cmHg. cmHg is just a unit of pressure, which basically all it means is that the pressure exerted by 1 centimeter of mercury. And 76 cmHg would correspond to 1 atmosphere, right? And similarly, you can have another unit of pressure, which is the mmHg, which is the pressure exerted by 1 millimeter of atmosphere, 1 millimeter of mercury. And that the mmHg and the cmHg are small units of pressure, so they are more convenient for measuring smaller pressures. You are all familiar with mmHg. Can you think about where you've seen mmHg? Well, if you measure your blood pressure, normal blood pressure you might be familiar with is 120 over 80. Where does that, what units are those numbers in? The answer is in mmHg. Okay. Hopefully it's clear to you how to convert cmHg into pascals. So cmHg just means the pressure of a column of mercury which is 1 centimeter high. So you would just use this formula H rho g. You would put H equals 1 cm. Rho is the density of mercury, and G, you know, is what, 9.8, and that would give you 1 cmHg in pascals. Okay. I have a problem based on mmHg in the next slide, which you can take a look at on your own.